Welcome to the Explainer. I am absolutely thrilled to have you here today. Okay, let's dive right into this, because today we're treating our mathematical journey like a genuine detective case. You see, we're stepping completely out of the comfortable, predictable world where standard rules apply, and we're venturing into the wild territory of oblique triangles. Think of this as a mystery where the usual suspects just don't fit the profile, and we're going to need a brand new set of investigative tools to crack the coder.
So I've got to start by asking you a really thought-provoking question. What actually happens when right angles go wrong? Now, in basic geometry, we get really comfortable with perfect 90-degree corners. We've got the Pythagorean theorem, we've got our basic sine, cosine, and tangent rules, and they all work like an absolute charm. But here's the truth of the matter. Perfect 90-degree right angles are actually quite rare in the messy, unstructured real world. Think about it. Mountains don't peak at exact right angles, right? And flight paths rarely form perfect corners. Most of the world is oblique, meaning the angles are either acute or obtuse. And the second those perfect right angles vanish, our basic trigonometric tools suddenly stop working.
So, to solve this little mystery, here's our roadmap for today. First, the cold case. Second, the master key. Third, case 1, the SS scenario. Fourth, case 2, the SSS scenario. And finally, case closed. Let's start with part 1, the cold case.
This right here is that wildly frustrating moment in trigonometry when the famous law of sines simply goes cold. Why? Because we just don't have enough evidence at the crime scene. Now, what's really interesting here is what's actually missing. Take a close look at these figures with me. Figure 3 gives us 3 side lengths, 16, 25, and a side labeled A, but no angles. We call this side, or SSS for short. Now, jump over to figure 1. Here we have an angle of 85 degrees sitting right between two known side lengths of 19 and a side labeled C. This is side angle side, or SAS. The core problem here is that the law of sines requires us to know at least one side and its exact opposite angle just to build a complete matching ratio. And in both SSS and SAS scenarios, we just don't have that matching pair. The trail goes completely cold. The triangle is, for the moment at least, mathematically unsolvable with our basic tools.
Which brings us to part 2, the master key.
Every good detective knows that when one tool fails, you just reach for a better one, right? Well, it is time to introduce our magical weapon and our brand new deductive tool to crack these unsolved cases. We call this the law of cosines. The definition you're looking at really empowers us. It's a geometric rule relating the lengths of the sides of a triangle to the cosine of one of its angles, specifically used when basic trigonometry fails. And I want you to realize right now that this isn't some scary, complex equation you have to memorize. It's actually just a reliable, mechanical recipe for finding the missing pieces of literally any triangle, no matter how slanted or skewed it might be.
Okay, let's just slow down the pacing for a second here and truly digest these formulas. This brilliantly illustrates the law of cosines formula in its 3 variations. Notice how they all follow the exact same rhythm? A squared equals b squared plus c squared minus 2bc times the cosine of angle A. Do you see the pattern there? It looks incredibly similar to the Pythagorean theorem at the very beginning, doesn't it? But because the triangle isn't a right angle, it has this brilliant adjustment piece slapped on the end, that minus 2bc cosine A part that corrects for the oblique angle. These 3 equations aren't 3 different rules. They're really just 3 different ways of relating all 3 sides of a triangle to one specific angle, totally depending on which side you're trying to find.
All right, let's dive into part 3, case 1, the SAS scenario.
Armed with our shiny new master key, we are officially ready to open our first case file, where we know 2 sides and the included angle directly between them. Let's walk through this methodology together as partners. Step 1. We carefully survey the triangle to identify our 2 known sides and that angle wedged right between them. Step 2. We plug those exact values into our law of cosines formula, making absolutely sure the side we want to find is isolated on one side of the equal sign. And finally, step 3, we simply follow the basic order of operations, simplify the math, and take the square root at the very end to reveal our missing side.
Let's actually put those steps into action. Look at the triangle on the right. We know side A is 12, side B is 10, and the included angle C is 48 degrees. We want to find side C. So the crucial point here is just choosing the right variation of our formula. We're going to use c squared equals a squared plus b squared minus 2ab times cosine c. Let's plug in those numbers. C squared equals 12 squared plus 10 squared minus 2 times 12 times 10 times the cosine of 48 degrees. Once you multiply that whole shebang out and subtract, you just take the square root of the entire result. And as you can see, the math cleanly simplifies down to our missing side, C,
being approximately 9.1. Boom, case 1 is officially cracked.
Moving right along to part 4, case 2, the SS scenario.
Now, let's jump into our second battle. Here, we face a slightly different obstacle, one that requires a bit more algebraic finesse. In the side-side-side scenario, we know all the boundaries, but absolutely none of the internal geometry. So our steps shift just a little bit. First, we identify all 3 known sides. Second, we substitute them into the formula. But step 3, this is where the real detective work happens. We have to use algebra to isolate the cosine of the unknown angle on one side of the equation. Once we've done that, step 4 requires the clever use of an inverse cosine function to finally unlock the angle itself.
Check out this triangle. It gives us all of its edges, sides of 5, 7, and 8, but absolutely none of its attitude. There are no angles anywhere. Let's say we want to find angle A, which sits right opposite the side measuring 7. We start with our formula. A squared equals B squared plus C squared minus 2BC cosine A. We plug in the numbers. 7 squared equals 5 squared plus 8 squared minus 2 times 5 times 8 times the cosine of A. Now let's simplify that. 49 equals 25 plus 64, which is 89, minus 80 times cosine A. We subtract 89 from both sides, giving us negative 40 equals negative 80 times cosine A. Then we just divide by negative 80 to isolate cosine A, which gives us 1/2, or 0.5. Finally, we ask our calculator for the inverse cosine of 1/2, and just like magic, the math reveals that angle A is exactly 60 degrees.
And finally, part 5, case closed.
I've got to congratulate you. By mastering these 2 specific scenarios, SAS and SSS, you've effectively upgraded your mathematical toolkit. Consider this slide your final detective cheat sheet, because it's absolutely vital to know not just how to use a formula, but exactly when to deploy it. If you arrive at a problem and you have angle-angle-side or angle-side-angle, you reach straight for the law of science. You have enough information to create that crucial matching ratio. But if you encounter a stubborn triangle that only offers side-angle-side, or the highly secretive side-side-side, well, now you immediately know what to do. You skip the law of sines entirely and confidently deploy the law of cosines to break the case wide open.
So, the takeaway here is absolutely immense. Mastering oblique triangles isn't just some boring exercise on a piece of paper. It literally means mastering the fundamental architecture, surveying, and engineering of the actual physical world around us. You now possess the formulas to measure things you can't even physically reach. So, my final question to you is this. Now that you have the tools to measure the unmeasurable, what real-world triangle are you going to solve first? Thank you so much for joining me on this explainer, and definitely keep exploring the angles of the world around you.